to a reference population. So he used kinematics to infer that most hot Jupiter hosts are actually typically relatively young, which perhaps indicates that hot Jupiters don't survive very long. Perhaps they are engulfed by their host star after a certain amount of time. Sam Grunblatt has looked at the dynamics of exoplanet orbits as a function of host star evolutionary stage, and he finds that evolved stars tend to host planets that lie on a period eccentricity relation. So perhaps over time, planet-planet scattering is driving eccentric orbits for planets that are far out, and star-planet interactions, tidal interactions, are causing orbits to circularize when planets are close in. So that's another evolutionary trend that's emerging. And then perhaps the trend that has received the most interest from the community is the evolution of exoplanet atmospheres. And in particular, we observe that young planets tend to be larger in general, and that these planets are losing their atmospheres through one or more mechanisms of atmospheric escape. And so there's a lot of interest in characterizing the time scale of exoplanet atmosphere loss so that we can understand what the driving physical process is behind that. And if I get time at the end of this talk, I will talk about that in a little bit more detail, but I'm not very optimistic that I will get there. So if I don't get there, you can ask me about it if you're interested. So, okay, I've mentioned that these are emerging trends that we're just starting to see, but this is still a very kind of young subfield within exoplanet science because stellar ages are so difficult to measure. And when I say ages are difficult to measure, what I really mean is it's difficult to measure ages for main sequence stars, which are the kinds of stars that we know host planets, with any level of precision. F and G dwarfs, yes, you can measure those ages with some degree of precision. K and M dwarfs, it's very, very difficult. And this is why, this is kind of a cartoon picture of why that is, which is probably very familiar to many of you. This is a stellar evolution track on the Hertzsprung-Russell diagram for the sun. And it's just illustrating why it's difficult to date stars when they're on the main sequence. When they're on the main sequence, they don't change very much over time. That's why there is a main sequence. That's why we see an overdensity of stars. And that is fantastic if you live around a main sequence star. It's very convenient for life, but it's very inconvenient if you want to precisely measure the ages of main sequence stars, which we do. So we have to turn to alternatives. Now, again, this is a track for the sun. For K and M dwarfs, it gets even worse. M dwarfs can have main sequence lifetimes that last trillions of years. So they really don't change very much over time in these observables. So there are alternative dating methods that we can use to try and get a better handle on stellar ages. What I've just mentioned would be described often as isochrone fitting, so fitting the position of a star on the color magnitude diagram to a stellar evolution model. We can also use abundances. There are some chemical abundances that show a trend with age. Typically, these are used as a kind of statistical measure of age. There's quite a lot of scatter still between elemental abundances and age, but we can use that to get a handle. Magnetic activity is often used as an age proxy, and it can be a great thing to use. In general, if you have a rotation period, that is a better age proxy than magnetic activity. Magnetic activity often gives you no additional information. It actually is telling you the same thing as the rotation period. But if you don't have a rotation period, magnetic activity can also be useful. There's galactic kinematics. So as stars get older, their orbits in the Milky Way change. Their orbits tend to become heated. They sort of orbit out of the plane of the galaxy more and more as they get old. If you have a population of stars that you think is coeval, you can measure the velocity dispersion of that population and compare it with other populations to assess, relatively speaking, how old or young is that population. That's something that we do quite a lot, and I will talk about that some more in this talk. There's astroseismology, which is kind of the gold standard of measuring stellar ages, but it's really not broadly applicable yet. It requires high cadence, high precision photometry for bright stars. We can't yet do astroseismology on M dwarfs. We have a few K dwarfs, but it's mostly F and G dwarfs and evolved stars. And so that leaves gyrochronology, which is the topic that I'm going to spend most of this talk talking about. And gyrochronology has the potential to be a very powerful dating technique if we can get the models accurate, because the rotation rates of stars change substantially on the main sequence. I mean, by an order of magnitude or more over billions of years. And we can measure rotation periods very precisely, and that's why gyrochronology can give us very precise ages for main sequence stars. And those ages get more precise as you go to lower masses. So a gyrochronology age for an M dwarf will actually be more precise than it will be for a G dwarf. But with that comes this very strong imperative to get the models accurate. Because if we're measuring very precise, inaccurate ages, that's not helpful for anyone. So in the rest of this talk, I'm going to go over gyrochronology, which is, again, the method of dating a star from its rotation period, which has sort of been around since the 1970s as a method, and for a long time was thought to be very simple. The relation between rotation period and age was thought to be a simple power law for a very long time, like up until 2019 or 2020. This is held up. Like many of my models are completely wrong. But we now know that this process is actually very complex. And so this talk is kind of comes with a warning. Like, if you want to measure an age for a star using gyrochronology, you really need to know what model to use, and you need to know what spectral type your star is, what rotation period it has, and this talk is kind of here to help guide that decision-making process. And I'm sorry to say that it's still kind of the Wild West out there, and it's still very difficult to apply gyrochronology, even if you know what type of gyrochronology model you should apply. Okay, so let me just explain in a little bit more detail how this process works and what gyrochronology is. So again, it's dating stars from their rotation period. These axes I'm going to show a lot in this talk. This is like the gyrochronologist's HR diagram. Rotation period on the y-axis, more slowly rotating stars are at the top, rapidly rotating stars are at the bottom, and effective temperature in reverse. So massive stars are on the left, low mass stars are on the right. And this is a model from Jen van Seders, which shows a kind of nice movie, an image, a picture, if you will, of how you can measure the age of a star if you know its rotation period and its temperature. There is a relatively simple relation you can read off of this graph. If you have the rotation period and temperature of your star, you can infer its age.
What's the physics behind it?
Good question. So this spin down is caused by magnetic activity and stellar winds. So stars are losing angular momentum through their magnetized stellar winds. Because stars are magnetized, the stellar wind is actually constrained to co-rotate with the surface of the star out to a distance, the Alfvén radius, which is set by the magnetic activity level of the star. So at that radius, a stellar wind particle will detach from the system, carrying away angular momentum. but up until that point, the wind particle is still connected to the star. So this means that a more magnetically active star will have a larger Alfvén radius and be much more efficient at losing angular momentum. And that's important because that explains why stars forget the initial rotation period they were born with. Stars start out with a rotation period that is usually kind of a random distribution between about a day and about 10 days. But by around 100 million years or so, stars have actually forgotten what rotation period they started with because of this mechanism. So a rapidly rotating star will have a large magnetic field because the magnetic field is generated by a combination of rotation and convection. So rapidly rotating stars have large Alfvén radii, which means they have large effective radii, and they're much more efficient at shedding angular momentum. Whereas a star that's born rotating quite slowly will lose angular momentum much less quickly, and the rapidly rotating star will quickly catch up to the slowly rotating star. And you can see that happening in this movie. At the beginning, there's a spread of rotation periods, and quite quickly the spread converges onto a single sequence. And that is why gyrochronology works. The angular momentum loss rate is proportional to the angular frequency cubed. There's a really strong dependence on the rotation rate of the star. So there's a convergence. This is why gyrochronology works, but this is a data-driven field. This was observed, then we created models to reproduce this. And this is all a very semi-empirical business led by data, and then creating models that have tunables that lead to us reproducing the data. And then just a reminder about how we measure rotation periods. So everything that I'm talking about today and in the lunch talk later today is relating to a photometrically measured rotation period. So we have high precision photometry of stars. Those stars have magnetic spots on their surface and they rotate, and that produces periodic or quasi-periodic variability in the light curve, which you can use to infer the rotation period. And a nice example of a beautiful rotation period, or a beautiful light curve which shows a clear rotation period, is this from TESS. You can see there's very clear quasi-periodic variability. We can apply periodic signal detection algorithms to light curves like this and pull out periods. It's not, of course, it's never as simple as that, and there's like a lot of, stars don't always look like this. This is a beautiful example, but for the most part, that's how we do it. Now, here is the distribution of stellar rotation periods. So this, again, is kind of like the gyrochronologist's HR diagram. It shows stellar evolution in the rotation period plane. And here it is populated with stars from Kepler in black and Mirth in purple. And this is kind of what the corpus of stellar rotation periods looked like up until about 2020. So let me just sort of explain again what's going on here. Stars move upwards over time in this space. This is a field population of stars, so they have a range of different ages, and that's why they fill out the space here. And canonical gyrochronology models look like this. So this is often described as Gyrokinematic style spin down, which is where your rotation period decreases as a square root of time. And this is what I mean when I say gyrochronology relations have been very simple up until now. A simple power law. We now know that models like this don't work for very many stars, actually. And there are some serious modifications that have to be made to this. So again, if you're interested in measuring an age for a star, applying Gyrokinematic will only get you so far. And it might get you a very precise and very inaccurate age. Okay. Now, I'm going to talk through all of the regions of this diagram where UMNH doesn't apply. And I will break this down in the next part of my talk. So for G dwarfs, there's something called weakened magnetic braking that you have to worry about. For K dwarfs, there's something called stalled or paused magnetic braking that you have to worry about. These names are all very similar, and so again, this is a reason why I'm giving this talk, is to make sure people are aware that these are different phenomena caused by different physical mechanisms, but they all apply. You have to be cautious of all of them. Another whacking great feature in this plot that I'm sure you've all noticed is that there is a striking gap in the rotation period distribution. And so I'm also going to talk about what we think is causing this gap and how you should deal with it. Then there's M dwarfs, which are doing a whole different thing. And then there's young stars, which again, you have to treat differently. So these are the regions of this plot where you can't apply UMNH. So don't apply UMNH anywhere, basically. But it's okay, I'm gonna help, hopefully by the end of this talk, I'll give you some references. So if you are interested in applying gyrochronology, you have a bit more information about where to go to find models that do work for all these different stars. Okay, so now I'll get into a little bit more what we think is happening in the rotational evolution of stars in all these areas of this diagram. Starting with weakened magnetic braking, which was really the first time any departure from UMNH had been noticed. Back in 2015, Jen Van Seders and myself, we noticed that there were some Kepler astroseismic stars, so stars with rotation periods and ages measured from astroseismology, which weren't lying in the right place in this diagram. So according to UMNH, they should have been up there, but they were actually down there. They were rotating too slowly for their age. They hadn't spun down enough. And Jen Van Seders has described this as weakened magnetic braking. And we observe that G dwarfs in particular seem to stop spinning down about halfway through their main sequence lifetimes. I want to show a sort of recent discovery that we made that supports this idea further. This idea has been around for quite a long time, since 2015, 2016, but it's been fiercely debated in the stellar astronomy community, and not everybody agrees that this is a phenomenon that's really taking place, because there are lots of biases in the data. Astroseismology has detection biases, rotation has detection biases, so it's been a little bit difficult to sort of really prove that this is happening. But Trevor David, a couple of years ago, was working on a sample of exoplanet hosts. This is actually the California Kepler survey sample of planet hosts. And he meticulously measured their rotation periods of the hosts. And these effective temperatures come from spectroscopy, from the CKS spectroscopy. He was not doing a gyrochronology project. He was doing an exoplanet project. But I saw this figure and I said, what is that? What is going on there? Is this a cluster? Or is it a sample of field stars? Because it looks to me like a cluster. Because there's a sequence, there's a tight sequence. So it looks like these stars are coeval, or at least some of them are. But in fact, that was not what was happening at all. These stars were not coeval. This is a field population of stars with all different ages. But what we realized was happening, now if you look back at the McQuillan rotation period sample that I showed earlier from Kepler, you don't see an overdensity of stars here. But if you swap out these photometric effective temperatures for spectroscopic effective temperatures, then you see very clearly that there is a pileup, a ridge line in this plane. These, again, are field stars of all different ages. So what's happening here is we think it's weakened magnetic braking. So G dwarfs evolve upwards on this diagram until they hit about halfway through their main sequence lifetime. And then it appears that they just stop spinning down. Now, this might seem like a big problem for gyrochronology, and I actually often find people saying, oh, gyrochronology doesn't work because of this. It actually only affects quite a small fraction of stars. It mostly affects G-dwarfs, and only once they get to halfway through their lifetime, by which time isochrone fitting actually doesn't work too badly for G-dwarfs. So this is not really, I don't think, a big deal for age dating stars. It does mean that you have to apply gyrochronology with caution to G-dwarfs, but if you want an age for a G-dwarf, a combination of gyrochronology and isochrone fitting will get you a pretty long way. And I would recommend using one of Jen Van Seder's gyrochronology models if you've got a G-dwarf. Yeah?
So the fairly old result called the Kraft break, is that the same thing as this? Or is
The Kraft break is sort of the temperature at which stars lose their outer convection zone. And so stars that are hotter than the Kraft break, hotter than about 6,250 Kelvin, just won't really spin down very much. There are some stars that are above the Kraft break here, and they don't spin down substantially. So the Kraft break is really it's a boundary in temperature or mass space. Did that answer your question? I'm not sure.
well, I mean, isn't a way you could interpret this just that you're seeing when stars are losing their convective envelopes and stop spinning down?
They shouldn't lose their convective envelope. So they stop spinning down at about the time when they hit a Rossby number of 2, which is about the same Rossby number as the sun, meaning their convective overturn timescale is about twice their rotation period. And yeah, these stars will remain partially convective, but we don't exactly know what's happening. Here's a cartoon of what we think might be happening. Somehow it seems that in the first half of the main sequence lifetime, these stars have active, very strong magnetic fields and a kind of dipolar field that produces strong braking. And then about halfway through their lifetime, once they reach this Rossby number of about 2, somehow they stop braking. Maybe that dipolar field is switching off. They still seem to have some magnetic activity that you can see spectroscopically, but they just appear to have stopped spinning down. And the mechanism, we don't know why this magic number, Rossby number of 2, is producing this, but that's, magnetic dynamos for you. We never really know what's going on, or at least that's the impression that I get. Okay, so that's weakened magnetic braking. Now, stalled magnetic braking. I've most commonly seen it called stalled magnetic braking. This is a completely different phenomenon. Now, let me talk you through it. So this shows a series of open clusters, and open clusters provide the majority of data that we use to calibrate the gyrochronology relations. They're lovely snapshots in time that show us the evolutionary march in period space, so longer and longer periods of these coeval populations. So there's, a blue cluster that's 120 million years old, spanning all the way up to 2.5 gigayears in red. And in Schumanich's time and for a long time afterwards, the data that we had to calibrate gyrochronology really looked like this. Open clusters with mostly G-dwarfs and the sun. But there's the Schumanich relation again. In 2020, Jason Curtis published this result, which shows something. There's certainly another departure from Schumanich, like spin down, a departure from this simple power law projected forward in time. So again, blue is a young cluster at 120 million years. Then we've got orange, 670 million years, Persepi. And then green, there's a gigayear-old cluster there the K dwarfs lie right on top of the younger cluster. The G dwarfs is still spinning down, but the K dwarfs seem to have temporarily stalled their spin down. And by the time you get to 2.5 billion years, stars seem to have resumed spinning down again, albeit with a kind of kink in the shape of the rotation period distribution, a sort of memory of this stalling. And now, why might this be happening? Well, the answer comes from Spada and Lansafami 2020, who model this phenomenon using core envelope coupling to explain why stars are stalling. So what we think the picture is stars that are spinning down here actually their envelopes are spinning down through weakened magnetic braking, but their core doesn't know all that much about what the envelope is doing and is continuing to spin quite rapidly. But at a certain point, the core and the envelope start talking to each other. We don't know exactly the mechanism for that, but it seems as though perhaps angular momentum, residual angular momentum from the core might be transferred into the envelope. The envelope is still braking magnetically, so the star overall is still spinning down, but the envelope is also receiving angular momentum from the core, and so the surface of the star seems to stop spinning down overall. And then eventually the core and the envelope will have coupled again pretty tightly. We know this is true for the sun, for example. And then we assume that a star will continue to spin down from then on as roughly a solid body. That's the picture that we have to explain this phenomenon. And the reason, again, why this is the picture is because models that implement this phenomenon fit the data. Again, it's a data-driven field. We observe phenomena, we tweak models. I say we. I'm not a modeler. I do the data, and so that's how we come up with our story to explain what's going on. So one other thing to point out with these clusters is that there are M dwarfs in these clusters that have not yet spun down to reach the single sequence relation between rotation period and age. So the art of measuring an age for an M dwarf is kind of a little bit less well determined, and we don't know exactly what age at which M dwarfs spin down, as in like what's the minimum age at which gyrochronology can be applied to M dwarfs. Emily Pass has recently published a paper on this phenomenon, and she, using wide binaries, finds that actually it looks like M dwarfs don't really converge until about 2 or 3 billion years. But we really sort of need more M dwarf data to kind of confirm exactly what's going on. So, as I mentioned, gyrochronology has been historically calibrated using clusters and the sun, a few astroseismic stars thrown in there, but there is a wealth of data from Kepler that is not being used to calibrate gyrochronology because we don't have ages for these stars. These are field stars. It's difficult to get ages for them unless you can apply gyrochronology to them. And we can't apply gyrochronology to them because there's no data up here to calibrate gyrochronology, so we don't have ages for these stars. And so a graduate student at Columbia that I've worked with a lot, Lucy Liu, and I came up with a solution to this problem where we use actually galactic kinematics to try and understand the ages of these stars so that we can then use them to calibrate gyrochronology. So let me just explain how we did that. For each one of these stars with a measured rotation period, Lucy grouped them with stars with similar properties, similar rotation periods, similar temperatures, similar magnitudes. And if two stars have a similar rotation period, temperature, and magnitude, they should be the same age. That's the central tenet of gyrochronology, right? So if you group stars together in that set of three-dimensional parameter space, you should be grouping coeval stars. So if you have a group of coeval stars and you measure the velocity dispersion of that group of stars, you can use an age-velocity dispersion relation to convert it into an age. And so that's what Lucy did, and that's how we're able to infer ages for these stars using kinematics with a weak dependence on the rotation period of the star. And Lucy calls these gyrokinematic ages because they are kinematic ages calculated using rotation period information. And Lucy is actually actively calibrating a gyrochronology relation now using clusters and these gyrokinematic ages for field stars, which is fantastic because it means we get calibration data up here at long rotation periods and old ages for low mass stars for the first time. And Lucy's actually, she's visiting soon, I think on the 21st, she's giving a CFA seminar. So I recommend going to check out her talk. She's going to, I think, talk about this and about galactic archaeology. Just to demonstrate that we do think these ages are accurate, let me show you this movie Lucy made. So this shows, again, rotation period versus temperature, and stars are colored by their ages or their gyrokinematic ages. The background sample there is the gyrokinematic age sample, and then these points with dark outlines are open clusters. This movie steps forwards in time and plots a line which is the average period at that age, and you should see that the line here, which is representing the gyrokinematic ages, falls quite neatly on top of the clusters and actually shows pretty incredible agreement, especially for these older clusters, including this one, which is M67, 4 gigayears old. The agreement between the gyrokinematic ages for field stars and that cluster is just incredible. So we think that these ages are really helpful for the community and for calibrating gyrochronology, and we're using them to explore all sorts of different interesting things in stellar and exoplanetary astrophysics. And for the first time, we can create this kind of time-lapse movie of how stars really and truly spin down and evolve in this space, in this period temperature space. So we don't need to extrapolate using models calibrated to young open clusters. We can just see in the data how stars evolve over time. Okay. I want to talk a little bit about the rotation gap because I think it has some more interesting stellar astrophysics, and because it's like this gigantically obvious feature in the rotation period diagram. And yeah, question.
Can I ask a question on the last thing before we...
Yeah.
So you mentioned that older stars are hotter than kinematics, makes sense? But
Yeah.
How is there some set of stars, old stars with known ages that calibrates the kinematics age relationship in the first place?
Yes. So there are a few different relations that calibrate a few different age velocity dispersion relations out there in the literature. Most of them, and including the one we use, has been calibrated using subgiants. So subgiants evolve very rapidly on the HR diagram. They're moving quickly in luminosity and temperature space. And so it is actually possible to get really quite a precise age for a subgiant using isochrone fitting to spectroscopic effective temperature and luminosity. And so usually age velocity dispersion relations are calibrated using subgiants. Okay. So the rotation gap. The rotation gap falls kind of close to where I pointed out stalled braking was happening. It's like around the K dwarfs and the M dwarfs. And so you might expect that it's related to that phenomenon. And so there's been a kind of a long search for the origin of this gap. It's very confusing and puzzling. It really stands out all the time. We figured that if we were able to measure rotation periods of fully convective M dwarfs and fill out this space a little bit more, we might be able to get to the bottom of what's causing the rotation period gap. Because if it is connected to stalled magnetic braking is caused by like an internal sloshing around of angular momentum. But fully convective stars don't have a radiative core. And so something different is likely to be happening to them. So whether or not the gap extends into the fully convective regime will tell us what's causing it. That's the idea. So again, this is work done by Lucy Liu. This is rotation period versus Gaia color. That's the Kepler sample again, and now in red. Now with clusters overlaid, and you can see, the clusters don't quite tell us what's going on in the gap because they fall on either side of the gap. And then the blue stars are the Mirth stars, rotation periods for M dwarfs. We wanted to fill out this space. Actually, originally we wanted to do it using TESS, but it's very difficult to measure long rotation periods with TESS, as if you come to my lunch talk, you'll see. And so instead we turned to the Zwicky transient facility and tried to measure rotation periods using ZTF light curves. And Lucy had a lot of success with this and was able to add these black stars to this distribution. She measured about 40,000 new rotation periods with ZTF. And you can kind of see by eye, but indeed, the gap does seem to disappear for late M dwarfs, for fully convective stars. And so this indicates that whatever is causing the gap is likely to be related to the fact that partially convective stars have separate cores and envelopes that spin down independently. And the fully convective M dwarfs just spin down continuously without ever stalling. Exactly why there's a gap is still not clear. Like, it could be that stars spin down, spin down, spin down, stall, and then spin down really quickly to cross the gap, transition really fast across this period range, and therefore the gap is unpopulated. Or it could be that stars, as their core and their envelopes connect, they perhaps become less magnetically active, and we just can't measure their rotation periods for stars that fall here. So it's not clear if the gap is truly empty or if it's a detection bias effect. That is still unanswered. But we can say with some degree of certainty that it would be a big coincidence if, we find in the fully convective stars the gap disappears, and it's not in some way connected to the fact that partially convective stars are spinning down with their core and their envelope separately. So we think we've partially at least solved this mystery.
So what fraction of stars in the relevant period range can you actually measure a period for? Is it most or a small fraction? Or?
With ZTF or just in general? Or?
Yeah, I guess either one of these data sets, right? Because if you're measuring most of the rotation periods, then it's probably not that there's a bunch missing, right? But if you're only measuring small fractions.
The recovery rates. Yeah. I guess it's difficult to know why a star is missing from this diagram. If it could be missing. If it's not got a rotation signal, it could be because it falls in this gap, or it could be because it falls up here, or it could be it's pole on, or it could be a weirdo that's not active, so it's difficult for us to know, I guess, why a star isn't appearing here, and to understand what our detection efficiency is, I guess. Yeah.
So a follow-on in the same vein, we all know the sunspots come and go on the sun on an 11-year cycle. For a few years here, one of our undergraduate labs that depends on sunspots had to not use them in the last cycle. So I'd be interested to know if ZTF data is a long enough baseline that you can kind of say what the recoverability is. Like for the ones that can't be recovered, you look 5 years later, then do you see?
Yes. I think it probably is long enough to do some of that. Like there's a few years of observations with ZTF. As far as I know, no one's looked into that.
Yeah, because I'd expect at least G stars, some year you might look at them and there's no way to get a period.
Yeah.
And 5 years later, it's easy.
Right.
Just, yeah.
I think there should be some more work on that, for sure.
I think the sun, if you look at it with ZTF though, even your maximum, the amplitude of the variation is too small.
It's too small.
For G stars, you have to do Kepler tests or something.
Okay,
like that.
Yeah, I think even with Kepler, the sun would be borderline whether or not you could detect a period, and certainly only in periods of maximum. I know, so I think people have tried to look at this a little bit with TESS. So for stars that are observed in TESS sectors that are separated by a large amount of time, to see whether the photometric variability changes. And I haven't heard much conclusive coming out of that yet, but certainly, there is a study with Kepler. Ben Monte has a result where he does find stars are variably variable on a cycle that looks like it could be a magnetic activity cycle. But ZTF could potentially be a better data set to do it with, because it is a little bit longer, I think, than Kepler. Not much longer, though, if it is. Yeah. Okay. I'm getting really short on time, so I'm gonna try and wrap up here shortly. I want to talk a little bit about M dwarfs because there's so much focus and attention on M dwarfs. M dwarfs are very cool in many ways. And JWST, of course, is searching for potential biosignatures in the atmospheres of planets orbiting M dwarfs. TESS is really focused on M dwarf exoplanets as well. And so it would be fantastic if we could measure the ages of M dwarfs with gyrochronology. I think that we're still not quite there, but we're getting close. And there's been a lot of work here at the CFA as well on M dwarf gyrochronology from Cecilia Garafo and Emily Pass and Amber Medina. One new result that I just wanted to flash up, I won't even say it's hot off the press because it's not on the press yet, but it's again another study led by Lucy Liu, so it will be on the press shortly, which shows rotation period on the y-axis. Now this is gyrokinematic age on the x-axis, with stars colored either in black or in red, according to whether or not they seem to be fully or partially convective, as defined by where they fall on the color magnitude diagram, if they're above or below the Zhao gap, which is this gap in the color magnitude diagram that separates fully and partially convective stars. This is a narrow temperature range of stars. What I want you to take away from this plot is just the fact that fully convective stars at the same age and temperature seem to spin down much more quickly than partially convective stars. That is what we're seeing in the data. And if true, this is pretty extraordinary. It's a very big difference. And so it maybe suggests that we need to treat fully convective stars really quite differently, apply different gyrochronology relations to them, which is, similar to what we saw with the gap result that I showed a few slides ago. Clearly, fully convective stars are doing something different to partially convective stars, and that's the takeaway from that. Okay, I was overambitious, and I have more material that I'm not going to have a chance to talk about. Let me just skip ahead. I wanted to just mention this for more context. I've talked mostly about Kepler and a bit about TESS and a bit about ZTF, but the incredible amount of data that we're going to get in the next decade for stellar rotation is going to really blow everything that we've already got out of the water. With Rubin, there's a potential that we could measure rotation periods for billions of stars out to incredibly large distances, like tens of kiloparsecs, perhaps even out to 50 kiloparsecs or something like that. And so gyrochronology becomes then a tool, an important tool for not just exoplanets, exoplanet populations, stellar evolution, but perhaps also for galactic archaeology. Once we can get out to these large distances with Rubin and map ages of stars across the galaxy, then it's really going to come to the forefront. So this is why the stakes are very high for calibrating gyrochronology, I think, because it's a very powerful technique. Stellar rotation periods is relatively easy to measure, precise to measure. Gyrochronology ages can be precise as long as we get the models accurate. That's the goal. Oh, I did promise that I would summarize this as well. So again, these are the regions that you need to use caution with if you want to apply gyrochronology. So if you have a G-dwarf, use one of Jen Van Seder's model. If you have a K-dwarf, use the Spada and Lanzafame model. Luke Baumer has a model that's coming out soon. Lucy Liu has a model that's coming out soon. M-dwarf gyrochronology, I would say there isn't yet a very reliable gyrochronology relation to use, but we hope there will be one soon. Young stars I didn't even talk about. This is maybe of most interest to exoplanetiers. Young stars, if you want to get an age for young stars, for a young star, you're best off combining multiple dating methods. And if you want a rotation age for a young star, the best thing to do currently is to compare it to the rotation period distribution of a cluster with a known age. Because again, there aren't great gyrochronology relations yet applying to young stars. Okay, let me just skip to my summary slide. Gyrochronology is perhaps our best hope for dating low mass stars. I am biased, but I think that this is certainly true for K and M dwarfs as far as I know. But be careful, because weakened magnetic braking and core envelope coupling complicate things, and you really do sort of need to know which one of these phenomena might be affecting your star so you can choose an appropriate gyrochronology relation. Fully convective M dwarfs might be doing their own thing entirely and need a whole separate gyrochronology relation. Young stars should be dated as an ensemble, ideally, or using multiple methods. But there's a lot of caveats here. Gyrochronology clearly has not reached the pinnacle of its potential, but I do think that it will be worth the effort with the billions of rotation periods that we might have over the next decade. I think there are some fantastic opportunities there. Okay, that's all I want to say. Thank you very much.
Okay, thank you for a great talk. Questions?
So you talked about single stars. We know that a substantial fraction are in binaries.
Yeah.
How does that affect the results?
Oh, terribly. That affects the results very badly. Yeah, binaries are right pain. So one good thing about binaries is if a star is in a very close binary, they'll be synchronized. That messes up the rotation period, but it will be a very short rotation period. So those are usually pretty obvious. What is a problem is if a star is in a binary that is separated enough to not be interacting, not be synchronized, but for the binaries to have disrupted each other's primordial disks, because disks cause disk locking and prevent stars spinning up too much in the first place when they're forming. And so secret binaries that are a little bit separated can look like single stars that are rotating more quickly than they should. This might not be too much of a problem, because once stars have reached a few 100 million years old, they should have rejoined that converged sequence. So it might be that this phenomenon is really still only affecting quite young stars who have memory of their initial rotation periods. That's a hope. But the real answer is that we don't quite know exactly all the ways in which binaries could be affecting things. And we see that gyrochronology works, so it can't be too bad of a problem. But certainly in any given star that's your favorite star, you probably would want to be quite certain that it is a single star if you're applying gyrochronology, or you want to be okay with having a certain number of your stars in your sample having an inaccurate age. So if you were doing galactic archaeology, for example, and you had hundreds of thousands of stars you wanted to date, then you might want to consider having something in your model that accounts for some fraction of those ages being inaccurate. You'd probably want that anyway, because rotation periods aren't always accurate measurements either.
Thank you.
That was really clear, so thank you, Ruth.
Thank you.
I have lots of questions for you, but can I limit it to two? One really quick comment is about the very last thing you showed, where the fully convective stars spin down more efficiently. That totally jives with the Zeeman Doppler imaging of the magnetic field structure, that they're surprisingly dipolar in fully convective stars and more complex in partially convective M stars specifically. So that kind of, the story stitches together.
Great.
If you're not aware of that work, I'm happy to point you to some
Yes, that would be great.
Okay, and the question is, what can you learn from differential rotation on these stars about the stalling mechanism? Is there anything that we can, if we could measure differential rotation, which messes up the rotation period measurement, but if you knew it, if you saw it was anti-solar or solar kind of differential rotation, what might that tell you?
That's a good question. I don't know, I guess I should repeat the question maybe for people on Zoom. The question was what differential rotation might tell us about stalling or might reveal about that phenomenon. That's not something that I thought about. It's a great question. I don't 100% know the answer to that. I haven't, there are certainly hints of us being able to measure differential rotation, but they're still quite hinty hints, I would say. Whether or not it's solar or anti-solar could tell us something profound about the magnetic dynamo, but maybe it doesn't, I don't know. It would be fantastic if we could reliably measure differential rotation. There is, I know it in the works potentially, Starry, which is a piece of software developed at the Flatiron Institute by Rodrigo Luga, is a tool that could reveal differential rotation in a large population of stars. So Starry maps, can map stellar surfaces. It struggles with single stars because you just don't have enough information about latitudinal and longitudinal star spot locations, but in an ensemble, you might be able to marginalize over the kind of degeneracies and produce something that's informative about things like differential rotation and about active latitudes on stars. And so that's sort of a project that we've been thinking about for a while at Flatiron, but we haven't found anyone to really take it on yet. But maybe there's hope there in the future.
Yeah, very, very nice talk, Ruth. So I was wondering, at the beginning you showed that there is like a bunch of different techniques to do this, right? And especially for the fully convective stars, do you think that there is an advantage to use more than one technique as additional parameter space, or where you can constrain things, especially things like galactic velocities and things like that?
Yes, good question. So the question was, would it be advantageous to combine dating methods, especially for things like fully convective stars? Yes, absolutely. And I know there are some people working on that. Rocio Kieman, for example, Ed Gillen. There is interest in combining dating methods. Some of them are very complementary. Like gyrochronology is very complementary with isochrone fitting, because isochrone fitting works well where gyrochronology doesn't, and vice versa. if you were able to combine information from abundances, from magnetic activity, from kinematics, from rotation, put it all into a big soup and get an age out of it, you would come out with a more informative, precise age, as long as your models are accurate. So you'd want to make sure that each one of those models was accurate, because where the models are informative, if they're inaccurate, they'll throw everything out of whack. And people do this informally a lot. They will infer ages from separate dating methods independently and compare and make a reasoned argument for what the age of the star is likely to be. You could take a more principled approach and do a joint fit using all of the input information you have, combining your likelihood functions from each of these different methods, and having a tighter posterior constraint on the age. And that is hard, but people are certainly working on it.
All right, thank you so much.
Thank you.